Let's start with what exponents and radicals actually are. An exponent is just a shorthand for repeated multiplication. When you see something like 2 to the power 5, it means multiply 2 by itself 5 times. That's it, a compact way to write a long product. Now, a radical is the reverse idea. If an exponent asks, what do I get when I multiply this many times? A radical asks, what number, multiplied by itself this many times, gives me this result? For example, the cube root of 8 asks, what number times itself 3 times equals 8? The answer is 2. The laws of exponents and radicals are simply rules that let us combine and simplify these expressions without doing all the multiplication by hand. They're like grammar rules for a mathematical language. You might wonder, why are we revisiting this in a calculus course? Because calculus is built on algebra. When you take a derivative or an integral, you often face messy expressions with powers and roots. If you can't simplify them first using exponent laws, you'll get stuck. For instance, the derivative of x to the power 3/2 is much easier if you recognize it as a power, not a square root. Also, many calculus problems involve solving equations where the unknown is in an exponent, like finding when a population doubles. Exponent laws give you the tools to bring that unknown down to earth. In short, mastering these laws now is like sharpening your axe before chopping down a big tree. It makes the hard work of calculus much smoother. Now let's see where these laws come from, starting from first principles. The product law says that when you multiply two powers with the same base, you add the exponents. Why? Because the exponent counts how many times you multiply the base. If you have 2 to the power 3 times 2 to the power 4, that's 2 multiplied by itself 3 times, then multiplied by 2 multiplied by itself 4 times. In total, you have 7 2's multiplied together, so the exponent is 3 plus 4, which is 7. This works for any base. The power of a power law says that when you take a power and raise it to another exponent, you multiply the exponents. Think of 2 cubed, all squared. That means 2 cubed times 2 cubed, which is 2 to the power 3 plus 3, or 2 to the power 2 times 3. So we multiply the exponents. Finally, radicals connect to exponents through fractions. Let's put this to work with a concrete problem you might see in calculus. Suppose we need to simplify the expression, the cube root of x times the square root of x. First, we rewrite each radical as a fractional exponent. The cube root of x is x to the 1/3 power. The square root of x is x to the 1/2 power. Now our expression is x to the 1/3 times x to the 1/2. Since the base is the same, we can use the product law and add the exponents. 1/3 plus 1/2 is a common denominator problem. 1/3 is 2/6, 1/2 is 3/6, so the sum is 5/6. Therefore, the simplified expression is x to the 5/6 power. We can also write it back as a radical, the 6th root of x to the 5th power. This is much cleaner and ready for differentiation using the power rule. Notice how we didn't need a calculator, just a clear understanding of the laws. You already know that an exponent tells you how many times to multiply a base, like 2 to the power 3 equals 8. A logarithm is simply the reverse question. Instead of asking what is 2 raised to the power 3, it asks 2 raised to what power gives me 8. The answer is 3. So the logarithm base 2 of 8 is 3. It's like a detective that finds the missing exponent. We write it as log, with the base in subscript, then the value in brackets. So log base 2 of 8 equals 3. It's just a different way of writing the same relationship between three numbers. Why do we need a whole new operation just to find a missing exponent? Because exponents let numbers get astronomically large, incredibly fast. A logarithm tames those huge numbers, scaling them down to something we can grasp. But the real superpower is this: logarithms turn multiplication into addition. Think about it. If you have 2 to the power 3 times 2 to the power 4, using the product law from exponents, you add the exponents to get 2 to the power 7. A logarithm sees the exponents 3 and 4, and when you multiply the big numbers, it just adds 3 and 4. This property is the secret bridge that made slide rules work and is why we use log scales for earthquakes and sound. In calculus, it lets us take derivatives of complicated products and powers by breaking them into simple sums. Let's derive these properties from the exponent laws you already know. First, the product law. Say log base b of m is x, and log base b of n is y. That means b to the x equals m, and b to the y equals n. Now multiply m and n. That's b to the x times b to the y. By the product law for exponents, we add the powers, it's b to the x plus y. So the logarithm of the product m times n is that exponent, x plus y. But x and y were just the logs of m and n. So log of a product equals the sum of the logs. The quotient law works the same way, but division subtracts exponents. The power law is a direct consequence of the power of a power rule. Let's use these properties to solve a real problem. Suppose you invest money at a 5% annual interest rate. How long will it take to double? The growth after t years is 1.05 to the power t. We want this to equal 2. To solve for t, we need to bring the exponent down where we can reach it. Take the logarithm of both sides. By the power law, the exponent t drops down in front, t times log of 1.05 equals log of 2. Now we can just divide. T equals log 2 divided by log 1.05. Using a calculator, log 2 is about 0.301, and log 1.05 is about 0.0212. Divide them, and you get about 14.2. So it takes just over 14 years to double your money. Imagine you have two numbers multiplied together, like 3 times the quantity x plus 2. Expansion means you spread out that multiplication into a sum of separate terms, 3x plus 6. Factoring is the exact reverse. You start with a sum, like 3x plus 6, and you look for a common piece you can pull out, turning it back into a product, 3 times x plus 2. They are two sides of the same coin, and together they let you rewrite expressions in whichever form is more useful for the problem at hand. Why do we care about rewriting expressions? Because in calculus, you constantly need to simplify things to see what's really going on. When you factor a polynomial, you can solve equations easily. If a product equals 0, at least one factor must be 0. When you expand, you can break a complicated expression into smaller, friendlier pieces, which is essential for taking derivatives. And when you're staring at a messy fraction in a limit problem, factoring often reveals a cancellation that makes the whole thing behave. It's like having a pair of glasses that lets you see the hidden structure inside an algebraic expression. Everything builds on one simple rule, the distributive law. It says that multiplying a sum is the same as multiplying each part and adding the results. A times b plus c equals a b plus a c. Expansion is just applying this rule repeatedly. Factoring is the reverse. You look at all the terms in a sum and ask, what's the biggest piece that divides evenly into every one of them? That piece is the greatest common factor, or GCF. You pull it out front, and what's left goes inside parentheses. Some expressions also follow special patterns you can memorize, like the difference of two squares. X squared minus a squared always factors into x minus a times x plus a. Recognizing these patterns saves you time. Let's use factoring to solve a classic calculus problem. Suppose you need the limit of x squared minus 4 over x minus 2 as x approaches 2. If you just plug in 2, you get 0 over 0, which is undefined. But look at the numerator, it's a difference of squares. We can factor it into x minus 2 times x plus 2. Now the fraction becomes x minus 2 times x plus 2 over x minus 2. The x minus 2 factors cancel, leaving just x plus 2. Now plugging in 2 gives 4. The limit is 4. Factoring turned an impossible problem into a trivial one. So the whole idea is, expansion and factoring are your algebraic Swiss Army knife. They let you reshape expressions to reveal the simple truth hiding inside. A rational expression is just a fraction where the top and bottom are polynomials. Think of something like x squared minus 1 over x plus 1. We call it rational because it comes from the word ratio. It's a ratio of two polynomial expressions. You've already seen factoring and expansion, now we put those tools to work on fractions. The goal is to make these fractions as simple as possible, just like you'd simplify 3/6 to 1/2 in regular arithmetic. In calculus, you constantly take derivatives and limits of expressions. If you leave a rational expression unsimplified, the algebra becomes a tangled mess. For example, the derivative of x squared minus 1 over x plus 1 is much harder to compute in its original form. Simplifying first reveals that it's actually just x minus 1, almost everywhere. This also shows you something subtle. The original expression has a tiny hole at x equals -1, where it's undefined, but the simplified line is defined everywhere. Understanding this hole is crucial for limits later. The process builds directly on factoring. First, factor the numerator and denominator completely. Here, x squared minus 1 is a difference of squares, so it factors into x minus 1 times x plus 1. The denominator is already x plus 1. Now you see a common factor of x plus 1 in both. Since it's a factor of the whole top and bottom, you can cancel it out, just like cancelling a common number. But you must note that x cannot be -1, because that would make the original denominator 0. The simplified expression is x minus 1, with that restriction. This is the core idea: factor, cancel, restrict. Let's solve a concrete problem. Simplify the rational expression x squared plus 5x plus 6 over x plus 2. First, factor the numerator. We need two numbers that multiply to 6 and add to 5, that's 2 and 3. So it factors to x plus 2 times x plus 3. The denominator is x plus 2. We see the common factor x plus 2. Cancel it, but remember the denominator can't be 0, so x cannot be -2. The simplified expression is x plus 3. To check, pick a safe number like x equals 1. The original gives 1 plus 5 plus 6 over 3, which is 12 over 3, or 4. The simplified gives 1 plus 3, also 4. It works. This same method simplifies any rational expression you'll meet in calculus. Imagine you have a complicated fraction like 5x plus 7 over x squared plus 3x plus 2. You already know how to add two simple fractions like 1 over x plus 1 and 4 over x plus 2 to get that complicated one. Partial fraction decomposition is just the reverse process. It takes a single rational expression and breaks it apart into a sum of two or more simpler fractions. The denominators of these simpler pieces are always the factors of the original denominator. So instead of one messy fraction, you get a handful of easy ones. Why would we ever want to take something simple and make it look more complicated? The answer is calculus. When you try to integrate a rational function like 5x plus 7 over x squared plus 3x plus 2, you get stuck. There is no simple rule for that. But if you first decompose it into 2 over x plus 1 plus 3 over x plus 2, the integral becomes trivial. Each piece integrates to a natural logarithm. So partial fractions turn an impossible integral into a sum of easy ones. This technique is also the foundation for things like Laplace transforms, which you will meet later in engineering and physics. Let's see where this comes from. Start with a fraction like 5x plus 7 over x squared plus 3x plus 2. First, factor the denominator completely. Here, x squared plus 3x plus 2 factors into x plus 1 times x plus 2. Because these factors are linear and distinct, we guess that the original fraction can be written as some number a over x plus 1 plus some number b over x plus 2. We don't know a and b yet, so we write them as unknowns. To find them, multiply both sides of the equation by the original denominator, x plus 1 times x plus 2. This clears all the fractions. You get 5x plus 7 equals a times x plus 2 plus b times x plus 1. Now expand the right side and collect like terms. The coefficient of x must match on both sides, and the constant term must match. This gives you two simple equations. Let's solve a concrete problem. Suppose a chemical reaction produces a product at a rate given by for x minus 2 over x squared minus x minus 6 grams per minute. We want the total product formed between minute 2 and minute 3. That is the definite integral from 2 to 3 of that rate function. First, factor the denominator. X squared minus x minus 6 is x minus 3 times x plus 2. So we set for x minus 2 over the factored denominator equal to a over x minus 3 plus b over x plus 2. Multiply out to get for x minus 2 equals a times x plus 2 plus b times x minus 3. Solve to find a equals 2 and b equals 2. Our integral becomes the integral from 2 to 3 of 2 over x minus 3 plus 2 over x plus 2 dx. Completing the square is a way to rewrite a quadratic expression like x squared plus bx. We force the x terms to become a perfect square, a bracket squared, and then adjust with a constant to keep the total value the same. Imagine you have an almost complete square made of tiles. You add a tiny corner piece to make a full square, then subtract that same piece outside so you haven't changed the total area. The result is always something like x plus a number, all squared, plus or minus another number. It's like repacking a messy sum into a neat square package with a little extra tag. Why learn this? Because factoring only works when the roots are nice round numbers. Completing the square works for every single quadratic, even when the roots are messy decimals or square roots. It's the master key. In calculus, we constantly need to know the vertex of a parabola, its highest or lowest point, because that tells us the maximum or minimum value of a function. Completing the square gives you the vertex coordinates directly. And here's a secret, the famous quadratic formula you might have memorized is actually just completing the square done with letters A, B, and C instead of numbers. So mastering this one move lets you solve any quadratic, graph any parabola, and even derive the formula yourself. Let's build it step by step. Start with x squared plus bx. We want this to look like x plus something squared. Recall that expanding x plus p all squared gives x squared plus 2px plus p squared. Compare that to our expression. The middle term bx must match 2px, so p must be b over 2. That means the perfect square we want is x plus b over 2, all squared. But when we expand that, we get an extra p squared, which is b over 2 squared, that wasn't in the original. So we must subtract that same square to keep the expression equal. The process is, take half the coefficient of x, square it, add and subtract that square, then group the first three terms into a perfect square. The leftover is always minus that squared half. Let's use this to find the minimum value of the quadratic x squared minus 8x plus 20. First, focus on the x terms x squared minus 8x. Take half of the coefficient of x, which is negative 8. Half of that is negative 4. Square it to get 16. Now add and subtract this 16 inside the expression. So we have x squared minus 8x plus 16, then minus 16, and finally the original plus 20. The first three terms factor into x minus 4, all squared. The constants combine, negative 16 plus 20 gives positive 4. So the expression becomes x minus 4 squared plus 4. A square is always 0 or positive, so the smallest it can be is 0, which happens when x equals 4. At that point, the whole expression equals 4. So the minimum value is 4, and it occurs at x equals 4. This method works for any quadratic to find its peak or valley instantly. Imagine an old-fashioned balance scale. On one side you have a mystery weight, and on the other side you have some known weights. The scale is perfectly level. Solving an equation is like figuring out exactly what that mystery weight is to keep the scale balanced. An equation has an equal sign, and it tells us two things are exactly the same. An inequality, on the other hand, uses signs like less than or greater than. It's like saying one side of the scale is definitely heavier than the other. So instead of one exact answer, an inequality gives us a whole range of possible values that make the statement true. In calculus, we are constantly hunting for special points. We want to know where a curve touches the x-axis, which is finding the roots of a function. We want to know where two curves intersect. We want to know the exact moment a rocket speed hits 0 at the top of its flight. All of these problems boil down to solving an equation. For instance, to find the highest point on a parabola, you first find where its slope is 0 by solving an equation. Inequalities are just as vital. They tell us where a curve is above or below the axis, which helps us understand the shape of a graph and find intervals where a function is increasing or decreasing. This is the basic toolkit for everything that follows. The golden rule is to always keep the scale balanced. Whatever you do to one side of an equation, you must do to the other. To isolate the unknown, you undo the operations around it in reverse order, like peeling an onion. If x is multiplied by 2 and then 3 is added, you first subtract 3 from both sides, and then divide by 2. This is just using our factoring and expansion skills in reverse. For inequalities, the rule is almost the same, with one critical twist. If you multiply or divide both sides by a negative number, the direction of the inequality sign flips. Think about it. 2 is less than 5, but if you multiply both by -1, -2 is greater than -5. A great way to see the solution to an inequality is to graph it on a number line, shading all the values that work. Let's solve a real problem. A ball is thrown straight up. Its height in meters after t seconds is given by the expression -5t squared plus 10t plus 1. We want to know, for how long is the ball higher than 3 meters? This is an inequality. We set the height expression to be greater than 3. First, we make one side 0 by subtracting 3 from both sides, giving us -5t squared plus 10t minus 2 is greater than 0. To find the boundary points, we solve the equation where it equals 0. Using the quadratic formula, we get 2 times, about 0.2 seconds and 1.78 seconds. The ball is above 3 meters between these 2 times. The total time is the difference, which is about 1.5 seconds. So the whole idea is that equations give you the exact moments, and inequalities give you the intervals in between. Trigonometric identities are equations that are true for every possible angle. They are not like regular equations that you solve for one special answer. Instead, they are always true relationships between the sides of a right triangle, the opposite, adjacent, and hypotenuse. Think of them as a set of reliable shortcuts. Just like the distributive law lets you rewrite 2 times x plus y as 2x plus 2y, these identities let you rewrite expressions with sine, cosine, and tangent into different forms. They are the basic grammar of trigonometry. In calculus, you will constantly run into messy expressions like sine cubed theta over cosine theta. Without identities, you would be stuck. But with them, you can swap that scary fraction for something simple, like sine theta times tangent theta. Identities are the key to simplifying derivatives and integrals. They also let you solve equations that look impossible at first. For example, an equation with both sine and cosine can often be rewritten using only sine, which you can then solve like a regular quadratic. They are your main tool for untangling trigonometric knots so you can apply the algebra you already know. All the most important identities come from one simple picture, a dot moving around a circle of radius 1. The dot's horizontal shadow is the cosine, and its vertical shadow is the sine. Because the radius is 1, the dot, its shadows, and the center always form a right triangle. The Pythagorean theorem, a squared plus b squared equals c squared, tells us that the horizontal shadow squared plus the vertical shadow squared equals the radius squared. Since the radius is 1, we get the bedrock identity, sine squared theta plus cosine squared theta equals 1. The word asine comes from an old word for a bowstring or fold, and cosine simply means the sine of the complementary angle. Tangent gets its name because it measures the length of a line segment that just touches the circle. From the picture, you can see that tangent is simply the vertical shadow divided by the horizontal shadow, sine over cosine. Let's use these relationships to solve a real problem. Imagine you want to know the height of a tall tree, but you can't climb it. On a sunny day, the tree casts a shadow on flat ground. You measure the shadow and find it is exactly 10 meters long. You also know the sun is at an angle of 30 degrees above the horizon. The tree, its shadow, and the sun's ray form a right triangle. The tree is the side opposite the 30-degree angle, and the shadow is the adjacent side. The ratio of opposite to adjacent is the tangent. So, tangent of 30 degrees equals the tree's height divided by 10 meters. We know from the geometry of a 30-60-90 triangle, which is half an equilateral triangle, that the tangent of 30 degrees is exactly 1 over the square root of 3. Multiplying both sides by 10, the tree's height is 10 divided by root 3 meters. That is about 5.77 meters tall. You already know how to expand something like 1 plus x, all squared, into 1 plus 2x plus x squared. That is exact algebra. But what if the power is not a nice whole number? What if it is 1/2, or -2? Expanding fully would give an infinite series. Binomial approximation is a trick that says, when x is very small, we can ignore almost all of that infinite tail and keep only the first 2 terms. So 1 plus x, all to the power n, is approximately 1 plus n times x. That is it, a simple, linear shortcut that turns a complicated power into a straight line. In calculus, we are constantly asking, what happens when something gets really, really small? We peek at a tiny change in x, which we call dx, and ask how much y changes. If we have a square root or a cube root, the relationship is a curve, which is hard to work with directly. The binomial approximation lets us replace that curve with a simple straight line near the point we care about. This is the entire idea behind a derivative, the slope of that line. So mastering this approximation now will make limits and derivatives feel natural later. It is the bridge from algebra to calculus. Let us see where this comes from. Take a power we know, like n equals 2. The exact expansion is 1 plus 2x plus x squared. Now imagine x is a tiny number, say 0.01. The first term is 1. The second term is 2 times 0.01, which is 0.02. The third term is 0.01 squared, which is 0.01. That third term is 10,000 times smaller than the second. So if we just drop it, our answer is 1.02 instead of 1.0201, an error of only 0.01%. The same logic works for any power n. The exact series starts 1 plus nx, and then every term after that has higher powers of x. When x is small, those higher powers vanish, leaving just 1 plus nx. Let us use this to estimate the square root of 1.04 without a calculator. First, rewrite the square root as 1 plus 0.04, all to the power 1/2. Here, our small x is 0.04, and n is 1/2. The approximation says this is about 1 plus n times x. That is 1 plus 1/2 of 0.04. 1/2 of 0.04 is 0.02. So our estimate is 1.02. The true square root is about 1.0198. Our simple linear guess is off by only 2 parts in 10,000. This same method works for cube roots, reciprocals, or any power. Just identify the 1, the small extra bit x, and the power n, and you have an instant, accurate estimate.